Problem sheet 6, question 5. A small fire department in rural Galicia runs 5 fire stations, F1, F2, F3, F4 and F5. These fire stations house 3, 1, 10 and 5 fire engines respectively. 2 calls come in simultaneously. There have been 2 major fire disasters, D1 and D2. The department estimates that D1 will require 14 fire engines and D2 will require 8 fire engines. The time in minutes from each fire station to the location of each disaster is given by the table below. By using the minimum cost method and then the stepping stone method, devise a plan for which fire engine should be dispatched to which disaster. Okay, we will set up the problem. We have 5 fire stations and 2 disasters. So that's 5 sources and 2 destinations. So we can set this up as follows. Disaster 1 requires 14 fire engines, Disaster 2 requires 8, and each fire station has a certain amount of fire engines available. And luckily there are 22 fire engines and 22 fire engines required, so we have equal supply and demand. The cost of sending a fire engine to a particular disaster will be the number of minutes it takes to get there. Using the minimum cost method, we will fill in the routes with the minimum cost first. So sending fire engines from fire station 3 to disaster 2 only takes 2 minutes, so we'll send as much as possible there. And we'll progress to the next smallest and the next smallest. We were expecting 5 plus 2 minus 1, so that's 6 basic variables, and we have 6 basic variables that are non-zero, so this is not a degenerate problem, but this is basic. Now we will use the stepping stone algorithm to improve this. So we will look at first at the route D1, F1. Our route here is like so. Then D1, F3. Our route here is this. Then we will look at D2, F2. Our route now is this. And finally we will look at D2, F4. Our route now is this. Of each of the non-basic variables, 2 of those, D1, F1 and D2, F2, would result in a more expensive allocation. 1, D1, F3. If we were to make that non-basic, that would not change the cost of the allocation. But if we changed D2, F4 to be basic, then that would reduce our allocation by 2 per unit or per fire engine we moved. Therefore, we will increase D2, F4 by, and how much can we increase this by? So if we were to increase, decrease, increase, decrease, our bottleneck is that we cannot decrease D2F5 by more than 4. So we will increase D2F4 by 4. Are there any more steps to take? So let's check again. So we will check D1F1. The loop now is this. How about D1, F3? The route now is this. D2, F2. The loop now is this. And D2, F5. The route now is this. And therefore the best action is to increase D1, F3 by how much? What is our bottleneck? So increasing D1, F3 would be to increase, decrease, increase, decrease. And so the bottleneck here is decreasing D2F3. We cannot do that by more than 1, so we cannot increase D1F3 by more than 1. Now let's see if there's any more moves to do. So we'll check again, D1F1. The loop now is this. D2F2. The loop now is this. D2F3. The loop now is this. And D2F5. The root now is this. And so the cost of making any of the non-basic variables basic are all positive, and so no more improvements can be made. We have finished the stepping stone algorithm, and we have found our optimal allocation of fire engines to disasters.